It's wonderful to be here. I've learned a great deal about the exciting research that Dave Marchant and his group are doing here. Let me start with some serious, not serious science. As an example of thinking outside the box, Hollywood's been thinking outside the box a lot longer than scientists have. Waterworld in 1995 with Kevin Costner, of course, when all of the ice on the planet melts and sea level rise goes so high that it covers everything on the planet. Not possible, but nevertheless, the idea that cities could very well be invaded not only by sea level rise, but by surges. And of course, as you know, had Hurricane Sandy hit Boston, you would have had certainly large parts of Boston would have been inundated. And the plan for Boston in a rising sea level is to make it into the equivalent of Venice. I'm not sure where BU is with respect to the Venetian canals, but certainly things to think about. But that's 1995. In 2004, The Day After Tomorrow came out, and it was actually patterned after a program that we had in central Greenland, where we discovered and verified the existence of very, very fast changes in climate, which we call abrupt climate change. It doesn't necessarily work this way. Again, Hollywood's exaggerated a bit, but that's what you have to do in order to make a point in this particular case. But these changes are dramatic, and we just experienced not this version of that change, but Arctic warming. And I'll tell you why Arctic warming is important and introduce you to the overall problem. So, thinking outside of the box, I'm going to focus primarily on abrupt climate change. Abrupt climate change is something we think about as having happened in the past because of the ice cores that several of us worked on. But in fact, as I just mentioned, it's just recently happened, number one, and it is every bit tied to extreme events. You cannot have abrupt climate change without having a series of extreme events of various types. And my big take-home message is we don't live in a linear world. Our lives are not linear. Everything that we do, everything we're involved in, it has at least some non-linear component, and it's well worth thinking about that, and in particular in climate. Like everybody else, I have tons of people to acknowledge. These include mentors, mathematicians, climatologists, archaeologists, a whole variety of people that I won't go through, but it's very important to remember that I'm going to show you a large volume of information. I didn't do all this myself. I was involved with a lot of other people and led a lot of other people. We're funded by many different organizations. The research that I'll talk about today primarily was funded by the National Science Foundation and the Keck Foundation. So, some of you, how many people here have been to Antarctica? Several of you. And you know this view as you fly in. That's Mount Erebus, the only active volcano in Antarctica, about 15,000 feet high. This is the edge of the Ross Ice Shelf. It's a floating mass of ice that comes off Antarctica, which is 1.5 times the size of the United States, on average about 6,000 feet thick. And this is something on the order of the size of a very large American state floating off into the ocean, creating city block size icebergs. So when you fly into a place like this, you are always taken with how vast it is, how remote it is, and in fact, when many of us, including Dave, started in the Antarctic, and I'm quite a bit older than he is, we all believed that Antarctica was timeless, and that this was a place that you go to because it's just a way to see a part of the world that has absolutely nothing to do with what we do in other parts of the world. Timeless, remote, and purely academic. Well, in the early 1970s, after I had gotten enough experience, I started leading expeditions across large regions of Antarctica. In the process, I was able to do more than 100 first ascents of mountains, cover tens of thousands of kilometers by skiing, snowmobiles, and then eventually heavy tractors. But in the early days when we did this, standing on the edge of the ice, on a portion of the ice sheet that's about 2,000 feet thick here, mountains poking up above, and small valley glaciers coming out, we realized that those valley glaciers looked as if they maybe weren't timeless. It looked as if perhaps they had changed in their dimension in maybe the last few thousand years, the last few hundred years. Then we started looking at snow patches from aerial photography and realized that things were changing an awful lot more than we thought. So we started to have a variety of studies looking at how fast the glaciers flowed, collecting ice cores, which I'll explain in more detail. But it was a big paradigm shift to think that even a place like Antarctica, so remote, so vast, ostensibly so timeless, in fact, was experiencing some amount of change. Well, in the early 70s, Antarctica didn't seem to me as if it was going to be a place that had any relevance to humans, although I continued to work there and still do for many years. And I thought that I would take the glaciology, the study of ice and past climate captured in ice, thought I would take it to a place where there were people. If you could study glaciers near people, then you had a good chance of coming up with something that would have value to people. You want to go to a place that has a lot of people, obviously the Indian subcontinent. And what I did, I'll show two slides that look like they are something that would be thrown out if you pass them in right now. But we did, this was a very intense figure that we produced in the late 70s that showed fluctuations in glaciers throughout the whole Himalayan period. And we were able to demonstrate that there were already by the late 1970s, we could document the fact that some of the glaciers in the Himalayas were moving retreating a lot more than we thought they would. And in looking through a lot of the old works that were done for the Himalayas, I came across Fanny Bullock Workman. She's a very famous climber from the early 1900s. There she is with her dress on. She did all of her climbing with a dress. And she made her way up to the top of Nun Kun in Ladakh. It had not been visited since then. And I looked at these pictures and I thought, because I was already involved in recovering ice cores, I thought this would be an interesting place to go. And eventually we got there and took this picture that basically shows we got to the same mountain that she did and that she characterized in the book. And in the process of getting there, which took 6 weeks just to get to the field site, we went through several villages, and this was the last village that we went through. This is the roof of their house. This is right on the transition between the Muslim region and the Buddhist region in this particular valley, very close to Pakistan. I managed to round up some of the locals. I was under the impression that they would know how to take me to the glacier that I wanted to go to, which was pretty naive because they had no reason to go to higher elevations. They barely could survive in the 2 or 3 months that the region was open. But eventually, with their help, with our help, we weren't allowed to have maps in this region, and we weren't allowed to have any form of communication. It was all taken away from us before we went into the region. We eventually made our way to the top of the Nun Kun Plateau up here, made our way up over 3 500-foot ice falls, carrying tons of gear, not tons actually, pile of gear up there, in order to see whether or not we could collect a viable ice core. And we saw, as we just crested over the top of the range, these dirt bands. This is 1980, and these dirt bands were a big find for us. It's not that other people haven't found dirt bands, but they were important to us because during the springtime, when the air masses come off the Tibetan Plateau and there's less snow in the Tibetan Plateau, this is dust that actually deposits every springtime and part of the summer. So this told us that that was a year's worth of snow, and we had the hope that we would be able to count back year by year. In 1980, this was a very big deal to be able to know year by year in an ice core. People had done it with tree rings for a long time, but they hadn't done it with ice cores. So we were interested in studying the monsoon, looking at changes in the wintertime input of air from the Tibetan Plateau, which is cold and dry, and the summertime air that comes off the Bay of Bengal and the Indian Ocean, and it's the interaction between this 180-degree seasonal shift in moisture that produces the Indian monsoon. And when there's too much water coming up from the Indo-Gangetic Plain, there's terrible flooding. Thousands of people can, in fact, perish. Not enough water, crops fail. Well, something very interesting happened in the process of collecting this ice core, which is the reason for this slightly longer story, and that is we saw air masses basically converging, coming from the Tibetan Plateau and the Indian Plains. Now, it stands to reason that an air mass would carry in it the things that it has blown over. For example, if it blew over the ocean, it might have a little sea salt in it. If it blew over the Tibetan Plateau, it would have some dust in it and a colder signal. Now, that stands to reason, but in science, you actually have to prove that things are true. And in order to do this, this was a particularly fortuitous situation. It was snowing like crazy, so we waited for it to stop, and then went from about 20,000 feet down to 10,000 feet, collecting fresh snow samples, and came back up to the camp. And this is the second, even less impressive figure that came as a result of that. This is from, I show in particular, because this is Geophysical Research Letters in 1983. You couldn't pass this into a class right now and actually have anybody pay attention. But captured in here is a very important concept, and that's the fact that the chemistry of these two air masses from the Tibetan Plateau and the Indo-Gangetic Plain actually have chemical signatures. And here is what NASA has done today to demonstrate this concept. They weren't worrying about it for the same reason that we were, but this is a video, obviously, of there's time chunking, clicking along right up here, and this we were working right over here, and what they've done is they've taken the air masses and they've colored them with the dominant chemistry of that air mass. In the Southern Ocean, this slight bluish white is sea salt that's being spiraled around in the low pressure systems that surround Antarctica, and sometimes they come in and invade parts of Antarctica, and that's basically warm air coming into Antarctica. In places like the Amazon, this greenish is of course biomass burning products that are making their way, they make their way all the way down every now and then onto this island called South Georgia, the one that Shackleton ended up on 100 years ago. The reddish here, and in particular coming off the Sahara, is dust that's blowing from east to west along with the easterlies, and it makes its way all the way into northern South America, and on occasion even into the Caribbean. And the stuff up here, unfortunately for us, this whitish stuff, is a lot of sulfur in the atmosphere. We've reduced the levels of sulfur, but nevertheless it's sulfur and a lot of other pollutants like lead mixing its way through the northern hemisphere. And we were standing right about here, 20,000 feet, when this air mass and that one came together. And now, of course, we have this beautiful image in a place for which we didn't even have a map in the past. So why would you care about chemically fingerprinting air masses? And this is one of the big points of the presentation, because if you know the source of that air mass, what it's carrying, it tells you the direction that it was coming from. You can actually relate it to the pressure systems that carry it. For example, in a low pressure system, the deeper the pressure, the stronger the winds, the more sodium comes in. And you can also tell how the strengths of these various emission regions, like deserts, oceans, biomass burning, volcanic activity, human activity, has changed over time. You could, for example, track acid rain, see if it's really coming from the northern hemisphere because of human activity or not. Once you've done that, if you know which way the wind blows, you also know where heat comes from, moisture, and pollutants. Now, in a greenhouse gas warming world, none of the physics of climatology changes. It's just that they're changing the heat that's being moved around. And we all know in this part of the world, when the air comes from the south, it's warmer. When the air comes from the north, it's colder. Not only that, but we know certain wind directions provide moisture, and for those of us who live on the East Coast, we know that pollution from areas to the west and to the north transport pollutants. In addition, if you know something about the history of air masses, you know which way surface currents are in the ocean are moving. It imprints a temperature into the sea surface, and vice versa. And when you take cold air and warm air and put it together, you get extreme events. Extreme events, droughts, floods, heat stroke, all sorts of things that we are being subjected to right now. So, why else would you care about the atmosphere? You'd care about the atmosphere because it is the primary way in which heat is transferred, not around the equatorial latitudes, but from about 20 to 30 degrees north and 20 to 30 degrees south, the primary way by which equatorial heat, which is of course where the sun strikes the earth most directly and which heats the most, and as that heat moves towards the poles, it is primarily carried by the atmosphere. And more so by the ocean close to the equator, but more so by the atmosphere as you get to higher and higher latitudes. So understanding which way the wind blows, what the history of that is, what the magnitude has been, turns out to be very important. We take our ice core records, which are nothing more than cylinders of ice that come from all over the world. I'll talk a bit more about it. And we can actually calibrate the ice core records with existing instrumental records. And in this particular case, it's a record from Greenland right over here, and we can come up with a proxy for the Icelandic low and a proxy for the Siberian high, which moves in this direction. And without going into a lot of detail, the instrumental record copies our proxy record or vice versa, explaining about 70% of the variance. That is very, very high. If you had 70% certainty about the stock market, you'd be super happy. If you had 70% understanding of the variance in a lot of things, you'd be very happy. The other thing that we do is we can take that calibrated record, so an overlap between, let's say, the last 50 years and year by year, season by season in ice cores that go back 50 years, and we can, once we come up with a calibration for it, we can go back through time. So we no longer have to worry, we no longer have only the instrumental record of the last 100 years at our discretion, but we have longer records that go back. And one of the interesting things that appears if you look at a record, for example, from a Greenland ice core from today back to the year 600 AD is a very, very fast change in the Icelandic low, this low pressure system over the North Atlantic that brings the nor'easters into this region, and the Siberian high, which pumps cold air in the wintertime into Europe. This fast transition occurred, I guess the text fell off, doesn't really matter, but this fast transition occurred, oh there it is, sorry, up there, marking the difference between the medieval warm period, our best analog for a warmer or warming climate. Arguably, we're probably at about that now, if not a little bit more, and the Little Ice Age, the underpinning for climate for the last 600 years, a time when glaciers were more advanced than they are now and colder. The other thing you can do is you can look at these records, and if you know something about the source of the air mass and you fingerprinted it, you can differentiate the starting times of, let's say, continental source dusts versus marine air masses. And without going into a lot of detail, this is that very same transition to the onset of the Little Ice Age. It's now the other way around. That's old, that's young. And it turns out that the terrestrial signal shows the onset of the Little Ice Age first. The Siberian high is over Siberia and the Tibetan Plateau, and that's telling us that the cause of this thing probably started over the continental area and then eventually spun up about 30 years later sufficiently to energize air masses over the ocean. So there are a lot of lessons to be learned by knowing which way the wind blows and how it's changed over time and the magnitude. And just to go through them very quickly, they include what's called abrupt climate change, which I'll expand upon. Acid rain, we collected a core from Greenland where we were able to demonstrate the existence of acid rain produced by humans. Changes in lead levels, changes in uranium. We just found 100 times increase in the last 35 years of the levels of uranium in the Antarctic Peninsula coming directly off Southeast Australia, open pit mining. Chernobyl, we were the first to identify Chernobyl in the southern hemisphere. The Antarctic ozone hole, we demonstrated that it's a relatively, the size of it today, relatively new phenomena. Water resources in places like the Andes, in particular Chile, which has a very, very narrow coastline. It is, or country, it is solely at the dependent on the existence of glaciers for water during the dry portion of the year and also for electricity. Arctic warming, which I'll focus on today, disruptions to past civilizations, which I'll mention, drought, marine productivity, etc., and a variety of other things. So once we figured out that these ice cores could be calibrated, that they could provide us with a history of what turns out to be temperature, precipitation, atmospheric circulation, sea ice extent, biological productivity, volcanic activity, forest fire activity, and on. The next goal was to find a site where we could get a long, well-dated, meaning year-by-year record. And this is now the late 80s. I was in charge of a program that had 25 universities in it. We traversed over parts of North Greenland to look for the right site. We had a collaborative program. This was the American program. That was a European program 30 kilometers away. We set up atmospheric sampling stations. But the bottom line is we set up a dome. This took us 5 summers. I spent 24 months total in the field. We put up a drill tower. We drilled down a little over 3,000 meters, 10,000 feet. And in the process, we collected a record. This doesn't look quite as exciting as that one, does it? We collected a record that goes back 110,000 years, year by year. And we broke up the core, this is a side view of the core, into a whole series of measurements. These are just the measurements that my lab did. And these measurements represent 95% of all of the dissolved chemistry that's in an air mass. So it gives you a lot of strength in terms of tracking air masses. And what we found was the following. This was the reason for things like the day after tomorrow, for this tremendous realization. In fact, we lasted longer in the press than a lot of small wars do, because this was such a tremendous paradigm shift. Prior to 1992, when our publications came out, we believed that the last roughly 120 years of global temperature looked like this: gradual cooling, fairly fast disappearance of large ice masses in the northern hemisphere, and then a rather dull-looking last 10,000 years, which is important because the climate that we live in today was basically started about 11,500 years ago, relatively stable compared to these cooler times. But we thought that the climate operated very slowly. That's a very important concept, because if the climate operates slowly, then it takes thousands of years to change it, and it doesn't really matter what you do. You could stuff CO2 into the atmosphere, you could do anything you wanted, the climate would change too slowly. Well, you've been no doubt looking down here, and you can see that that doesn't turn out to be the answer. Places like Greenland, there are these very, very fast changes in temperature, even during what appears to be this less variable in terms of temperature period of the last 11,500 years. And there are tremendous changes in the strength of North Atlantic and other storms. So we discovered massive shifts in storms, precipitation, temperature, some cases 15 degrees centigrade, that occur in less than 1 to 2 years and are sustained for decades, if not centuries. We explained it's a consequence of 2 things. One has to do with ocean circulation, but I'll talk about the one that operates faster. That's atmospheric circulation. And this is a cartoon of the jet stream. This is the air mass that, when you go from California to the East Coast, allows you to go an hour and a half faster because you're moving with the westerlies. And the jet stream, in its winter position, it's roughly here. The shape changes. It's very important to remember that. And it divides cold air from warm air. And then during the summer, the divider moves farther north. And we determined, and I'll show you quickly how we did that in a very simple way, that this thing actually snaps in less than a year or two from one position to the other and stays in that position in general. It's the equivalent of taking the winter in Boston, which lasts, 2 months, and suddenly making that winter 10 months long in less than a couple of years, sustaining that in general with variability for decades to centuries. So this is operating faster than a political cycle, which is quite remarkable, and it also has dramatic impacts. In this plot, I've taken the terrestrial and marine chemistries, and it turns out that they pretty much all have this shape over the last 110,000 years. Why does that matter? That tells us that the air masses were well mixed, and for air masses to be well mixed, they must be very strong, and they must be moving over land and ocean. So this was actually a model for these are called zonal winds, zonal westerlies, when they basically move along a line of latitude. We also found some chemistry which was particularly coming from nitrogen compounds that demonstrated whenever we saw those nitrogen compounds making their way into Greenland, that told us that air masses to the south, because there wasn't much biological activity to the north in these polar regions. These are pulses of biological activity making their way northward. So with these time series, the understanding that, in fact, what I was showing you here are changes in the size and shape of the polar vortex. Remember in 2014-15, everybody's talking about the polar vortex. This is one configuration of the polar vortex, and this is another configuration of the polar vortex. So the next thing that we were able to do with these highly detailed year-by-year records was understand what in fact forces climate, and more importantly, what is capable of creating these fast changes. And in the natural climate, here's what the data set looks like. You can break it down into a relatively identifiable pattern statistically. And one of the things, of course, that controls climate is where the Earth is with respect to the sun, but that operates on scales of tens of thousands of years. It's not going to create an abrupt climate change. If you were to play around with the levels of the greenhouse gases, that could trigger a fast change. If you could change the way heat is transferred around in the ocean, the so-called thermohaline circulation system, by, for example, adding some fresh water in one place in the North Atlantic, changing the density and therefore changing the heat transport in that area, that would be another thing that could trigger abrupt climate change. Ice sheets can only get so large before they become unstable, or other things begin to destabilize them, and you can have these massive changes in ice sheet extent. There's Mount Erebus again, and change the numbers of icebergs that come out into the ocean, which changes the color of the ocean, the absorbance of incoming radiation, and also the transmission of long wave radiation. You can change the energy output from the sun. There is a solar cycle, but there's people talk about a solar constant, but the energy flux from the sun, in fact, is known to vary. And as it varies, it actually changes the ozone concentrations in the upper atmosphere. Ozone is O2 with an oxygen, making it O3, and it's trapped typically between about 10 and 25 kilometers up in the atmosphere. And it is what protects us from incoming radiation. When you have an ozone hole, a lack of ozone, much of that radiation can strike the surface of the Earth. It's the reason that we don't get as terrible a sunburns as we could. And if you take all of the ozone in the upper atmosphere from 10 to 25 kilometers, compress it, it will make a layer of about this thickness. So there's not a lot of it, and it's really easy to destroy. And it changes in accordance with the solar cycle, simply because of changes in incoming UV radiation. Dusts, this happens to be an example from the Dust Bowl, but there are obviously also natural reasons for having dust, and volcanoes. These are all, everything with a red star could potentially by itself or in combination create an abrupt climate change. How many of these things do humans actually have the ability to influence? Well, clearly, greenhouse gases. And in fact, if you take a look at greenhouse gases using the ice cores that are being recovered from East Antarctica that go back in excess of 800,000 years, we know that the variability in CO2 over that time period is within a relatively small envelope, which we have exceeded dramatically and will do so even more by 2100. But what is not only important, the magnitude's not only important, but the fact that the rise in temperature in the last few decades is 100 times faster than anything we can detect back in this time period. That's big. All of a sudden, you're taking CO2, a known forcer of climate, and basically injecting it way, way faster than it had been before. And then, of course, there's methane, which we're beginning to learn, we being science, learn more and more about. And it's effectively the elephant in the room because it has about 30 to 60 times the heat trapping capacity. And this brings us again back to Arctic warming. There's a tremendous amount of methane trapped in the permafrost. And as that begins to release, which is starting already, there are parts of the Arctic where you can go literally dig a hole in the snow, light a match, and it'll burn because there's methane that's emitting. So another trigger are dusts because of poor agricultural practices, because of urbanization. A secondary trigger is the melting of places like portions of the Greenland ice sheet because of greenhouse gas warming that input fresh water and change the heat balance or the heat distribution of thermohaline circulation. Another secondary effect is water moving into crevasses along coastal areas in places like Antarctica. As that water freezes, it literally explodes, causing relatively thick, 50, 100 meter thick ice shelves to basically be broken away from their connection to land. Another thing that we have played around with, the sun, through its changes in energetic particles which impact ozone, we also impact ozone, in particular in the Antarctic, because of the production of humanly engineered chemicals, which has been reduced, but it's going to be several decades before those they've gotten out of the atmosphere. There are also other things we emit that are not so well regulated: nitrogen compounds, certain types of sulfur compounds, chlorine compounds. They all destroy ozone. Not the way the sun does, but they impact the ozone cycle. So the bottom line is, when we begin to think about these linear models that are delivered to us by IPCC, Intergovernmental Panel on Climate Change, which is a remarkable document because it gives us a phenomenal basis for understanding the climate system, they don't necessarily take into account abrupt change or a series of multiple abrupt changes. Why not? Because the first truly well-defined abrupt climate change event that has occurred in the last 100 years is Arctic warming. And so we'll focus on that and a couple of other things. Now let me just slide back a little bit. The other thing we looked at in this Greenland record was the length of the summer in the last 10,000 years by taking a look at the extent of sea ice, which in general today is where the white line is, but in the past, even in the Little Ice Age, it potentially got out that far. And if you take a look at the length of the summer, you see that longer summers, there are some pretty prominent events that are time periods when there were longer summers. In particular, 4,200 years ago, a very, very sharp onset of a long summer, absolutely consistent, demonstrated by several of us and others in various different ways, leading to the collapse of the of what was the Mesopotamian Empire, which is modern-day Syria and Iraq. A very similar thing happened, a shift of air masses, also in the coincident with the collapse of the Mayan Empire. It's really comes down to something as simple as, if the moisture-bearing winds are not coming in during the wet season, then you don't have water, and that's the end of a city. Water is our most important commodity, and that's exactly what happened in the Mesopotamian Empire and in the Mayan collapse. These were abrupt shifts in moisture-bearing winds that no longer got into those areas. IPCC has suggested that all of these areas in reddish and orange are at risk of major drought by 2070, if not earlier. They're already participating in drought. So one of the things we were able to do was to demonstrate, yes, absolutely true. In the past, if you look at places like the Middle East, the former Mayan Empire, yes, when you have longer summers, this is exactly what happens. There are many of us who believe, and this is a big point in the Years of Living Dangerously, a long TV series, a film series we were involved in, that the underpinning for the Arab Spring comes from drought, and sustained drought. So if you look at the more recent record, remember we talked about Little Ice Age starting 600 years ago, AD 1400. One of the most interesting things about that comes from Greenland. The Vikings the Norse made their way to Greenland in about 1000 during a time when the summers were rather long. They stayed there a few hundred years, created cathedrals. They did all sorts of European farming, never adapted to the local Inuit ways of life. And AD 1400, with that abrupt climate change, they were cut off with sea ice. They could no longer be supplied. But that provides so here the Little Ice Age is actually the underpinning for modern climate. And yet in the last few decades, we've experienced this tremendous warming. So that begs the question, if we were not doing what we're doing, would we in fact still be in a Little Ice Age climate? And if in fact human activity is offsetting the Little Ice Age, you might think that that's a good thing, but it's not a good thing. If the natural climate would like to be a little bit cooler, you're superimposing warmer conditions, you're basically creating even more extreme events. So Now let's turn to the global record of temperature going back to 1880, about as far back as the well-recorded records go. But in truth, most climate data sets, they're called climate reanalysis because of the way they're smoothed over the planet, start about 1979, pretty close to the onset of the satellite era. So this is where we have the best confidence. There has definitely been a significant warming trend. You've read all about these things. Is this the full story? Not entirely. This is the real story. This is the distribution of that global rise in temperature over the planet. And in this particular plot, this comes from software that we've developed in our institute called Climate Reanalyzer. I suggest you take a look at it. It's a great way to teach yourself climatology, learn how things have changed. But if you look at, for example, the last 20 years compared to the previous roughly 15 or 20 years, what you will find is that the greatest amount of warming has happened in the northern hemisphere, and the greatest amount of warming actually happens in the high latitude of the northern hemisphere. And there are even parts of the world that are cooling. The Southern Ocean is experiencing some amount of cooling. These are all consistent with what we've done to the atmosphere through changes in greenhouse gases and ozone, which is also a greenhouse gas, but we tend to think about it separately. Despite the fact that one is resulting in warming and one is resulting in cooling. You can see that the primary warming is really in the high latitudes, certainly along the coast of Antarctica. And here, this is pretty wild. The Southern Ocean, for this time period compared to the earlier time period, is actually experiencing some amount of cooling. Let's focus in on the Northern Hemisphere. If we take a look at the time period 2007 to 2012 compared to the prior record going back to 1979, we see that the difference in temperature in the Northern Hemisphere, this annual temperature, is quite remarkable. It turns out to be as much as 8 degrees Fahrenheit in the eastern Arctic. 8 degrees Fahrenheit, 5 degrees centigrade is as big as many of the abrupt climate change events that we were talking about in the early 1990s in the GISP record. And to translate that into something that's probably that has a bit more relevance, if you translate it into annual melting degree days, which is actually a way of looking at the length of the length of the summer in the eastern Arctic and a couple of other places is 100% longer in this 5-year period than before. We have experienced a dramatic abrupt climate change event, which I'll talk more about in a little bit. So let's see how do these temperature changes actually impact atmospheric circulation. If you have a warming Arctic, absolutely clear. Some amount of warming in the mid to low latitudes. What you've actually done is flatten the temperature gradient. This normally should be cold, that should be warm. As you flatten the temperature gradient between the poles and the equator, the winds run perpendicular to this temperature gradient. That means that the westerlies begin to weaken, and as the westerlies begin to weaken, you weaken the barrier between cold air and warm air, and you have much more exchange of air from the south, which is warm, making its way farther north, and from the north, the cold air making its way farther south. What does that do to the winds? Well, it weakens the winds in the northern hemisphere. In this purple area, these numbers look really low, but they represent 10 to 20% drops in wind strength of the westerlies in the northern hemisphere. And if we take a look at how these wind patterns translated into shapes of the jet stream, what do they actually look like when you look at the at temperature and places that we live? If you look at basically the general change in temperature in the northern hemisphere, this red circled area, since about 1979, it's a little bit less than a degree centigrade rise. If you take a look at change in the Arctic temperature, another way of showing what I showed you before, we have about a 3 degree centigrade rise in that short time period. But if you go to Eastern North America, particularly in the year 2014-15 winter, although there have been times when the temperatures have gotten as much as 2 degrees centigrade higher, it's been highly variable. It all has to do with the shape of the jet stream. And in fact, almost Christmas, I like to say Christmas, although it was December 30th, at that time the jet stream looked like this. There was a big cold tongue that came down. That cold tongue allowed warm air to move up Next to it, and 30th of December 2015, the North Pole was above freezing. Remember, it's dark up there. It's nighttime up there, and yet the temperatures were above freezing because the jet stream is able to take cold air much farther south, warm air farther north, as a consequence of Arctic warming. And these are just some examples of that. You can see how amazingly embayed some of these things are. They shift. Sometimes they get locked over eastern North America. Sometimes they get locked in other places. So in order to demonstrate how significant a change this is, we had a program called the Asian Ice Core Array. We went all over Asia, took the existing records, collected double the number of ice cores. This is Mount Everest. We've done 5 seasons on Everest up at about 24,000 feet. And put all those records together, and very, very quickly we were able to show for the last 500 years, which is as far as these records cover, that the strength of the westerlies has actually been weakening over Asia. Just as was demonstrated for the last 20 to 30 years, that 20 to 30 year period is in fact anomalous. That weakening of the, let me say this again, this weakening of the last 20 to 30 years is relatively anomalous for the last 500 years. So let's go to the southern hemisphere quickly. Remember warming along the edge of Antarctica, but there's very strange cooling along the surface ocean. And turns out it has a lot to do with the Antarctic ozone hole. There is an Arctic ozone hole, which is actually helping to change sea ice extent in the Arctic. And if you look at the Antarctic, because you've lost ozone, it's actually allowed, and because the continent is very high, you actually have lost a lot of heat that's in the sort of middle atmosphere. Greenhouse gas CO2 is warming the mid to low latitudes. The net result is that the temperature gradient here is flattened. The temperature gradient here is actually steepened. That makes the westerlies stronger. The stronger the westerlies, the more cold air is trapped in south polar regions and separated from warm air, and you get very little exchange of air back and forth. In effect, the Antarctic ozone hole is helping to protect Antarctica, not the coastal edges, but the rest of it. And here's the proof. If you take a look at the last few years compared to the previous years, this shows you the change in wind speeds. They're increasing on the order of 15 to 20% in the Southern Ocean, and when you increase wind speeds over the Southern Ocean, you drag surface ocean water forward, and cold water from below comes up, and that's why parts of the Southern Ocean are in fact cooling. The net effect in a place like southern South America is this. These are the winds, increasing wind speeds in this area around Cape Horn. And the net effect on temperature is actually, as I mentioned already, cooling, because you're pulling up deeper, colder water, and it's making its way farther north than it normally does. And the proof here is the fact that there are actually penguins that are migrating northward along the eastern coast of South America, following those cold currents. But again, it's a consequence of human activity. So to get a record from Antarctica, giant place, understand how it's changed, I organized 21 countries. We've traversed thousands and thousands of kilometers all over Antarctica. We developed, as we did for Asia, a record. This one goes back 10,000 years, demonstrating that turns out since about the middle 1800s, the circulation system, and this is a proxy for this westerly circulation and this other little giant low pressure system in here, is in a very unique situation compared to at least the last 5,200 years. And around 1850 is the beginning of greenhouse gas rise. So we're seeing even a change in the thermal gradient as a consequence of that. Why is Antarctica important? Why is ozone important? As you begin to change the ozone hole and begin to fill it in, which will happen in time, it'll heal. You'll change the wind patterns around Antarctica. You change this low pressure system, which I just pointed to. All of those things have a lot to do with how much moisture goes onto the Antarctic. Many people believe that sea level rise could be partially offset by taking precipitation, putting it onto Antarctica. It's not happening yet, but it also allows warm water and warm air to make its way, well, depending on where this westerly system is, it can or cannot allow warm air and warm water to get closer to the edge of Antarctica, which changes CO2 balance and a variety of other things. These two pictures represent the two possibilities for the future, in my opinion, of the Southern Hemisphere. One of these is a system in which the winds around the Southern Hemisphere remain fairly zonal. They run along lines of latitude, and this will continue to protect Antarctica. There'll be warm marine air masses that make their way into West Antarctica, but in general, Antarctica will be locked off. The one I believe is true is more like this one. It's a system in which warm air masses make their way, and warm water makes its way farther south, and basically the westerlies or the jet stream it's not zonal, it doesn't run along latitudes, it bumps in and out. And there are examples of this in the last few years that may in fact be precursors. If this is true, tons of warm air goes into Antarctica and you have even faster sea level rise, more collapse of ice sheets, and a lot of changes to the Southern Ocean. So the next thing we wanted to do was to see, learn more about this change in the Arctic. In fact, how unique is this change in the Arctic? If you take a look at the modern record, just a few more to go through here, you can see that there were times, this is changes in temperature, summer, annual, and winter from 1960 roughly to the present. You can see that there are times in the Arctic when there were almost little warm pulses, which would have, of course, had less sea ice. There's almost the implication that there are precursors, times when the climate system in the Arctic looks like it wants to get warmer and has less sea ice, but then it can't quite do it. It tries again, and then these precursors are critically important. The way that we predict the largest atmospheric phenomena on the planet is through the El Niño Southern Oscillation, and there are indicators in the ocean and in the atmosphere that tell us that the conditions might be right for one. We can't predict abrupt climate change events yet. We can look back at this one and say, yeah, it ended up in an abrupt climate change event, but it'd be good if we could actually predict them better. So what we did is we changed the field of ice core science, and instead of producing data that has about 1 centimeter resolution, which in some cases, when it's very compacted, turns out to be 1 sample a year, we've now gone to 120 microns, so about 10,000 samples per meter rather than 100 samples per meter. This is the system, without going into a lot of detail. It's a laser ablation system. It actually looks like a little worm that's making its way along, and that's an ice crystal. We have a microscope with a video attached to it, and you can actually see whether or not the cracks have different chemistry, and you can get a large amount of detail. And so we focused in on, this is going back to the GISP record. These are the cold times up here. And there is the transition out of the last major cold time, almost the last resurgence of the Ice Age, going into modern climate, the Holocene. It's called the Younger Dryas Holocene transition. And that's the record. That's a blow up of the record. And you can see for the original sampling, our chemistry was on the order of about 10 centimeter resolution sampling, which is, for the time, it was state of the art. It was phenomenal. It took us 5 years to do the analyses. Now, we get 10,000 samples a meter. In the first day that we ran this system, we collected more data than I had collected in my entire career. And in fact, I will guarantee you, we collected more data than not only my career, but several other people who do exactly the same thing I do. So talk about big data for our field. It's just a giant change. And this is the detailed data itself. But the big point is that this is the spacing of the years. The peaks are basically winter, spring during the Younger Dryas. The years, the amount of snow deposited, this is the compressed version, was only 1 centimeter during the Younger Dryas, and then precipitation increased by 3 times as you get into the Holocene. And you can see that within a year or two, there is this very dramatic change from very short summers to very long summers. The summers are the flat eras in between. This translates into well, it's a doubling, as it turns out, in the length of the summer. And of course, that's what we've just experienced, is a doubling in the length of the summer. Now, that younger Dryas Holocene transition didn't just affect the eastern Arctic. It affected a very, very large area. But the bottom line is that the magnitude and the speed of change that we have just experienced is similar, although less areal extent, to what we experienced at the transition from the end of sort of the last ice age into modern climate. Big. It puts it in perspective. So the Arctic is critically important. We would like to be able to look at more of these abrupt climate change events to look for precursors. There are several ways to do it: climate modeling, looking at teleconnections, the things that atmosphere components that are connected. We've developed these new climate tools that allow us to look for modern analogs. What does a warmer climate in the last 100 years look like compared to a colder climate, and past analogs from ice cores. These are the areas that we're working on right now. We have field programs in almost all of these areas to look at, obviously, Asian change in climate. We've recently done a program not with ice cores, but for USAID, looking at predictions for drought in West Africa. And one of these places, and this is where I'll end very quickly, is right here. This is the last expedition that I did. My team, we do ourselves about 5 or 6 a year, but this is one I did last October, and we'll do again next October. We traveled from the tip of South America, flew to the Falkland Islands, and from the Falkland Islands made our way to the island called South Georgia. South Georgia is important. That's where Shackleton ended up exactly 100 years ago after his ship was crushed in the ice. It's also important because it gets air masses from quite far north in South America, and because it is surrounded by the most productive fisheries in the Southern Ocean. People don't quite understand why they're so productive, and because it could give us a climate record that tells us about the South Atlantic, which can be gotten from, at least in ice cores, from nothing else. So that was the conclusion of what we call the West Wind Expedition in 2015. We'll be going back in 2017. That's our form of transport. It's a 74-foot sailboat. That's the entire team plus 2 members of the crew that stayed on board. Everybody sails the boat, not with the same expertise, but this is 1,800 miles of Southern Ocean sailing. The boat's 74 feet long. The waves are 60 feet high sometimes, and the winds get up to 60 knots. And this is just a remarkable, remarkable aluminum boat that you can go beating right into the waves with. It allows us to make our way around icebergs so that we can eventually take a small inflatable, make our way up onto the island the same way Shackleton did. Turns out he found by accident the best route up the island, haul our sledges up for a few days into the plateau regions, do the ice coring, and come back out again. So I'll end with that. Thank you.